All right. I think everybody's here, so we can maybe start. So today we're going to start off with Conor, who's going to be talking about some of his recent work on non-staging and processes. He's focusing on regression. So the idea is that Conor will give about a 45-minute talk, and then we'll have some time where we can discuss afterwards how this can maybe be used in invasion optimization or some ideas, but mostly everything. So the idea is kind of talk and then a discussion after. So Conor, thank you very much.
Hello. Yeah, so thanks for coming. Yeah, so as Rita said, most of my work really is on regression using non-stationary and de-Gaussian processes, but we're going to front load this a little bit and talk quite a lot about stationary and de-Gaussian processes generally, and then we'll get some technical stuff at the end, and we can spend as much time as necessary on So what we're going to talk about, we'll talk about problem formulation, Gaussian process progression in general, maybe, and then we'll talk about non-stationary Gaussian process progression. It's a little like subjects inside this as well. Everyone's from quite a mixed background, so if there's anything that people don't understand, just do chat. So the problem is quite a simple one. We've got a load of data points, UI, and we've got an unknown function f, and we have the value of this function called data point, and we want to recover this function. So the function f might be expensive or difficult to evaluate, so it might come from a time simulation or some sort of chemistry experiment. So I'm kind of assuming most people know about the Bayesian framework, but this is essentially what we're doing in it. We're going to put prior on the function f, and the likelihood, and then from that we're going to get posterior back conditional on y. It's not exactly like this, like in Clary's talk yesterday. Obviously, we're working with functions, so we think dimensions, so we've actually use the rate on predicting derivative and stuff like that. But this is how we can picture it. So yeah, from the Bayesian framework, we have all these advantages that we have on set. Problem. What we want to look at is posterior consistency. So we want to look at as the number of known data points n goes to infinity. Does the mean actually converge to the function that we want to look at? Does it work? So I'm going to list an introduction to Gaussian processing. So Gaussian processing is just a stochastic process such that if we take a finite distribution, we have a normal distribution. So we write a Gaussian process like this. It's completely defined by its mean function and its covariance function. I'm assuming we don't know what Gaussian process is, but so what we want to do is we want to take this Gaussian process and we want to condition the function f on these known values y to get a posterior mean, which is also a Gaussian process. So the advantage of the Gaussian process is you can do these updates and you still have a Gaussian process at the end. We can find explicitly what the posterior mean and the posterior covariance is. So here, I don't think we worry too much about that, but it's more there. So this is kind of what we're doing in the conditioning process. We take a prior distribution here, just quite a week prior with the mean going through there. There's some samples that we've taken to the mean. Can you see this like fluid region? That fluid region is 2 standard deviations from the mean at a specific point. And then when we do our update, what we'll do is these purple dots, known data points, and what we're doing is we're essentially squeezing together. We're also assuming we don't have any noise here as well. Let's see if we have noise again. variance with not zero around these points. But this is like the function we're trying to cover here in x. And anyway, so we know what the value of the points that we're pinching together with the prior distribution. So what we want to do is we want to use this Gaussian process prior. We're going to select the mean from 0 all the way through. And we're going to look at what we can pick for this covariance for A. And that's going to completely describe the Gaussian process for us now. Now we've got the 0. So this K, this kernel, reflects the properties of that, or we hope that it's going to reflect the properties of that. So if we, for instance, this is a Gaussian kernel, which is also the term kernel with a regularity parameter of infinity. So this means that the sample smoothness, and you can see here that we just played around variance of sigma squared, the lambda length scale. Nothing, I will just play around with the if you thought the function was going to be very flat like this and have no changes, you pick that lambda with that. If you think that relations. This is all well and good. If the function f that we want to recover is stationary, so that means basically it behaves similarly in different parts of its domain. But this is just a simple example of where it doesn't work so well. So if we have a non-stationary function, so on the left we have this very smooth modifier, and on the right we have this step function. So we can see really what we would want to do with my length scale is very flat here. And then here we're going to make a big change. And this is using the Gaussian kernel. And we can see that the length scale that we select, we can't basically select the length scale that will activate this file. So essentially the problem that we want to solve is we want to somehow vary the length scale over our input domain. So these are three options for kernels that we can pick to vary the length scale over the input domain. First one is a warping of the domain, so it's like a homeomorphism on an input space. The second one allows us to use multiple stationary kernels and change the variance of this domain. We'll go into all of these in a bit more detail as well. And the third one is this lambda relates to this length scale here, this lambda, say, in the stationary kernel. So it allows us to basically, instead of having a constant lambda here, it allows us to vary the domain. You can see how this could be useful in this point. Okay, so these are just some examples of how the kernels might work. So this is for the warping kernel. So this is a domain, and if we use this, so these are just for examples. I don't know what real world configuration this is going to look like. But you can see that if we use this warping function of delta, you can see it's like you can imagine it somehow being actually this line. Let's squeeze that up there. It is, but So you can see really that if you look at the covariance between these two points in your regional parameter W, they will be the same, but with this W function, highly simple, or much more kind of large length scales over here, because the range decreases. I was trying to look for an example for this one, but this one's a bit of a strange example, but stay with me a little bit. Because so if you have on one half of your domain, you have a function that is continuous, but its derivative is nowhere continuous, but on the left side of your domain, a complete smooth function for some reason. You can define this, so you define two kernels on your domain, but you create variances, so the variances get large ranges. So like a smooth kernel on this side of your domain and a non-smooth kernel on this side of your domain. Maybe this is right. But maybe there's nothing happening, and all of a sudden there's an earthquake that then goes on forever. Thank you. But yeah, you can see also this chain comparison of the same now prior distribution across that. And the final so the final example is for the convolution kernel, and this is varying the length scale. So you can see actually, so this is a 2D example, and you can see this is value of the function cross here, and you can see that over this domain -1 to 1 box. So you do have varying length scales over the domain. You have more dark or flat regions, and then you do have regions where so you can create. So these are just priors, but you can. So we haven't actually conditioned on any data yet. So these just are priors, but you can see that you can actually create these like non-stationary priors using these three functions. I think there are other functions, but these just two. No, yeah, that's a really good point. That's the issue, because you don't know the lambda a priori. Like if you knew, say you wanted for this one, here, there's a lambda that would work very well, but if you knew what that lambda was, then you wouldn't know what the function is. Or maybe, like it would be a lot of information, extra information you have. So you need a way to learn. So the first half of this is based on we kind of have convergence, we have rates and these convergences if you know what the lambda is beforehand, which in practice you wouldn't necessarily do. And then the second half of this is how you use the Gaussian processes to learn what the lambda is. Yeah, I mean it's just like which was hierarchical model. Yeah, essentially. But so that's what we're because that is the issue. You need to learn the numbers are. It's all well and good happening. Okay. So, oh, sorry, was there any more questions on you? So we're actually going to look now at what convergence rates we can get. So do they actually converge? Like if we use these as the prior distribution, of the kernel in the Gaussian process for the prior distribution, does it actually converge in the end? So recall that we want to observe that this predictive mean in the Gaussian process tends to act as the number of known data points going to infinity. So the predictive mean, it turns out, is actually a linear combination of kernel functions. So actually what we're doing is a radial basis interpolation here. So we're going to use this to borrow ideas from, essentially what we're doing here is static data approximation. So really we're going to use ideas from numerical analysis to prove this. Yeah. Is that yeah, because you set the errors to 0. Yeah, so so in practice, what you have to do is you have to add like a nugget to them or something to be able to do this. In practice, exactly, without any noise. In practice, if you try and compute this, you can't compute this in verse. So So in practice, you do actually have to add noise when you're implementing it. Because otherwise, when you're doing this in inverse, there's no chance. So in practice, you do add like small. You add as little as you can to get away. Okay, so the convergence properties will actually depend on the choice of kernel K for the width. So in terms of how we look at how many data points we've got and how this will affect us, we define this, which is the fill distance, which is also the minimax norm, which is just the maximum of the minimum distances between any of your known data points and the points in your domain. So the uniformly spaced points, this is roughly scaled. So amongst one over K. So don't worry too much about the details of this, but each kernel K has an associated reducing kernel Hilbert space. So we've got the definition of it down here, which we can go through if people want, but really what we need to think about here is it's just it's a Hilbert space where if you're close in the norm of the Hilbert space, then you're close point-wise as well. So the results for the non-stationary Gaussian process regression are we split them into two types. So we either have error bands where the function f that we're trying to recover is in this reproducing common space, whatever it is. Or we have error bands where the function f is in some Sobolev space, and we can show that the reproducing common space for the term k is actually equivalent to the Sobolev space as a vector space. So they both have their pros and cons, I guess, these two. One of the things for the native space is great because it works for every level, or it's very general. But the big issue really is that it's often unclear what this native space actually is. So yeah, so this is the definition I find it down here. So you can definitely find functions in it by just taking some span here. So you know it's not, but yeah, it's quite fine. If you can find it, so sometimes we can actually show that it is Sobolev space or equal to a Sobolev space as a vector space. So if we can do that, then it's better. So in this sense, we have clear assumptions on F, which is good because we know a lot about Sobolev spaces. I said this actually, that some people know a lot about Sobolev spaces. Like as a community, there is stuff known about Sobolev spaces. But there is restrictions on A, obviously. So I'm not going to go into this too much because there's quite a lot of information there. But the thing I just wanted to yeah, you end up needing equivalents for the particular. Yeah, maybe for some, but yeah, for these you do need the equivalents, you need it both ways. Because essentially it relies on this idea that for the Matern term, the reproducing polynomial space is a Sobolev space, or is equivalent to a Sobolev space that relies on this to make this. You do need equivalents both ways. Yeah. I mean, you get some of the you don't get it all the time. Well, say for instance, like I mean, if you knew the value, if your domain was the same size as, yeah. But say in this example, you always get these like patterns. This one.
No, it doesn't work. It doesn't, it doesn't work.
Wait, yeah, this is right. So yeah, there's a lot there, but basically the point of this is that the rates that you get depend on both the number of derivatives or the smoothness of your stationary kernel and the smoothness of this like non-stationary function. Like, so the smoothness of W, the ends which represent your variance, which is changing the margin variance rate, and the number which represents your next step. That's just what H is this so you can just think that H goes to 0 as you go.
Think about optimization of the optimization environment. Yes. I'm not sort of, I don't have a good intuition for all the norms that we're using. Can you derive sort of pointwise bounds on pointwise differences at the points from these bounds so that you can say, I will make only an error of if I use this to sort of interpolate my objective function. I only get an error of say epsilon, or how many points do I need before I get an error of epsilon at any point in the interval that I care about. And you divide bounds like that from these bounds, just that I get a rough intuition. Or do you think this is sort of intrinsically hard because you're sort of hiding intervals beyond these sort of points? I honestly don't know. That's why.
Well, it is. So you mean in a certain in a certain part of your domain? So you're looking for like your optimizing and
or maximum error that I get over the whole domain. And you bound that with this type of estimate, people assume that you can. Yeah, that's fine, but
yeah.
I would be interested in seeing here.
Yeah.
Okay,
This is
okay. Okay, but no. Okay, but you say this is.
This is just so you're deterministically picking your points beforehand, and this is over your whole domain.
Yeah, good.
Yeah.
I just wasn't aware which one this actually is.
Yeah. Oh yeah, sorry, I should have said so. The C one is the.
Yeah, perfect. And everything's great. Okay, perfect. Thanks.
So also, this is in terms of the if F is in this native space, which we don't know that much about, but instead we want to look at in Sokolov space, which we again not we people know well right. So actually, this is what I was saying to this. Now that for the return kernel. So I don't know if everyone knows what the return kernel is, but essentially it's just the kernel where you can vary the regularity of the domain. And this new here tells you an example. So that's equal to a Sokolov space, and we can use this for both the mixture and the warping construction. To basically show that the reproducing Hilbert space that comes from the warping and mixture kernel is actually equal to a Sokolov space as well. We use these kind of nodes here. I'm not going to go into this either, but this is another example of the norms of the bands that you get. So here you see that depending on the regularity of the return kernel, which noise you have, and the regularity of the variance, marginal variances in your mixture component thing. That's how it is what bands or what we're not going to read this. If you want to read this, you can read it in excruciating detail. That would be probably a use. So let's. So these just have the joint for example to show that you get the convergence rates. So this is for the mixed covariance with only one L. So we've done this mixed covariance with all together, but we've only taken one of them, and we've taken it's actually well, the mixed rate is 2, we have 2.4.
They're also not like you get to show. Doing like thinking of like put a screen down to function between your, but that's really not a key. But in your case, you're bound. I mean, but the trick there is that you assume that the function is actually inside the referential field. That's the assumption.
Yeah. So you actually see. So we have numerical examples that show if the function is out, but still get those rates as well. But yeah, but for the theory to work, you have to see it.
I mean, are they more like big or small? I mean, I know those are subjective, but they can be used. Basically, would you be able to use them if some kind of dynamic?
Yeah, well, I guess if it's if you're talking about solid spaces, then yeah, definitely. In terms of the, I don't actually know if we make the space for the kernels. We don't know what the maker space is. So the issue really that we had is that we've got these non-stationary kernels with these non-stationary functions in W, lambda, M, etc. And that's all well and good, but yeah, as Sebastian was saying earlier, it's not clear how we should pick these lambdas, how we should pick these W's. So one method to do this is using the Gaussian processes. So the Gaussian processes are a sequence of functions that are conditionally Gaussian. So F0 is just a sample from a Gaussian process with some kind of stationary invariance kernel. And then, so that's our bottom layer. And then one layer up from that, we condition this. We condition this kernel there on the sample that we've taken from the previous layer. So the kernel is somehow dependent on some previous layer, and then we have the sample we take from that layer conditioned on the layer below is Gaussian. So the examples that we had previously are DGPs with two layers. So you have your bottom layer, you think of sampling it, and then your bottom layer would then go into your lambda or your W somehow, and the layer above is your statement dependent on the layer below. So this setup does allow for variety of instructions, so specifically back to and I stop it in mistaking. Actually we saw this, I think we saw this. But these are just examples of some samples that we can get from these data. So this is again not conditional data. And it seems like the top layer here is smooth, very stationary. And then as we go down, you get the areas of narrative up here with smoothness there, and you get narrative here, you see something very, very different here. So I'm so sorry, I feel that it's pretty sad. I'll go back to the first level. But we want to get some conversion rates. So basically what we're trying to do is we're trying to condition on the data, and then our estimates will come from the top layer. So to do this, for example, the mixture with the character 1. So we've got a mixture, but we've just got variance times the kernel. As before, we have naught to be a sample from the Gaussian process with mean 0 and some return the variance kernel. And then for the next layer, we use the variance kernel of the mixture kernel, where Fn now, or with some link function, takes the form of the variance of the function. So this variance, there we go. So we want to then use Fn, where we said that Fn is the top layer. This is the data, and this posterior Fn 1. And what we're interested in with this top layer still is if the number of known data points goes to infinity, do we get convergence? And basically under suitable conditions, we still get convergence. The convergence depends on the you pick, because every time you take a sample from the Gaussian process with the return kernel, the sample has slightly less regularity. So every time you take a sample, the regularity decreases. So it depends on the number of layers that you have and on the regularity of your kernel at the beginning. So we get similar convergence. Well, no. Now you don't have anything, but now using MCMC. But you don't have anything in closed form. So now, now we're using, we don't have anything in closed form.
It's double layer. It's the whole thing.
Yeah.
All the layer of the thing.
Yeah.
You can see some of the difference from all layers.
Yeah. Yeah. So there's for instance, yeah. So this is what you're doing if you want to recover this stack on. And you want to layers. This is us doing it for the one process that, and then for two layers. So really what you're inferring from the top layer, what you're inferring from the layer below, 1 over this particular set. So you can do one scale very high in the point square and use it. Right, different for the layers, and I can't do it. Another layer to it, but that's not. That, no, that's not. Eric, story, or looking at the one, the paper that they read, yeah, it is enough. Yeah, I think this one. On the function. You for what? Sorry, for the to get the regs, or just. I guess it won't work for any function because you need to set up your process, and still have to the kernels so that it would work. So I think this goes back to the same issue with trying to smooth things. Yeah, well, so basically you can show that, yeah, a lot of the time no, but under really certain circumstances, you can show that they are solvable spaces. That we using current level spaces, they're associated to them. But you have a lot of restrictions on your so it's essentially it's just in the same. So with the non-stationary ones, just non-stationary, not deep Gaussian processes, as long as you select I don't know, the non-stationary kernel in the correct way, you can show that it's a solid space, the solid space, and that's basically the same that you do with deep Gaussian processes. You just do it inductively. But yeah, it's quite tiresome. In general, no. Oh yeah, so this time, so basically it's the same thing. So you can construct in there about you can do the walk and sure, one. You can also get this other construction of deep Gaussian processes. Why Gaussian processes? See about that. Which is essentially the same idea, except that you don't have just one sample from your bottom layer that goes into the next layer. You take multiple samples and then put that into the next layer. Then you use this mixture formulation. You only do it for Gaussian processes. Yeah, future direction. So whereas we can show for the raw thing and for the mixture kernel that the ingredient kernel space is equal to the solid space, we can't do that because the convolution kernel at the moment. So that would be a nice thing. And so we do have quite well, not that type of restriction, but we would like to have less restrictions than this mixture function. And also continue to have it. I actually got it black. Awesome. You for listening.
More on the I mean, not full practice, I mean, the thing that Gaussian process was the way to have a hyperparameter strictly all the whole function.
Yeah.
Is there any simple ways of having a hyperparameter that would allow you like okay, for example, your examples that you have for like places where you have one behavior to another behavior, so you actually have a parameter that gives you the switch.
Yeah. So there are like other ways to do it. There's ways where you can split up your domain and use different. You can actually just split your domain and use different kernels and different parts of your domain. You can do like tree Gaussian process. There is various other ways.
Yeah, but are they amenable to the theory of your theory, or are they
oh yeah, well, so well, oh, so you yeah, I mean, with these estimated parameters, so you estimate them beforehand.
No, I'm just
Sorry.
And then the second question I was regarding so I see how, for example, a step function really has different regularities in this function. But when you only give data, then it's very difficult to know whether you choose something the step function, but it's a function with a very steep gradient. And so it is actually infinity, but it has just a very strong gradient. I mean, your results in some sense are symptomatic results. Yeah. Are they, I mean, it's kind of overkill in some sense because I mean, in practice, we're never gonna get to be able to distinguish between the various gradient and an actual chunk.
Yeah. So is it overkill to do that? Yeah.
I mean, I'm just saying that it's the eternal question that I mean, well, my work is actually the same question for you. But it's an asymptotic result in the sense that
I guess there are a lot of new ones where the next goes to the check. It's not really a step. Certainly the length gets changed very well.
yeah.
It's usually prior.
But on the other hand, you could work. I think it's just because we're switching between the theoretical results and then practically using it. And if you want to train them on data, then you use even to be more data because you not only need to get like the concept, but also the switching the ranks and so.
Sorry, I didn't hear.
I guess if you're allowed to choose, I guess then you can get to your own design, and then you can then sort of target your evaluation of if you have a situation where you evaluate one area where you want to learn the
Yeah. Yeah.
in terms of distribution.
So I was thinking, I mean, basically, again, training something, I think.
Yeah.
Observation. That's basically, I think, for
When it's the mean, yeah, it's the mean for distribution rather than realizing.
Yeah. I am because
Yeah.
So if the rates are getting, I mean, that's an ideal one, you know, that someone has to go. Yeah, then so now so there's no being put in suboptimal or
That is the rates optimal.
well, let's say no, I mean, no, let's say, you want to know the results.
Yeah.
Like, what is it?
Yeah. Yeah.
Would that then that's some funny thing that you would report, or is that really fast?
I think
That you get some more rates because basically what it's not the cost, right?
yeah.
Probably something.
I think in certain circumstances definitely suboptimal. I don't know.
There's underlying that. You want to live there and see it's
Yeah. Yeah. So you use the same boot.
Well, that's what we from the north there.
Yeah. Yeah, that's true. Yeah, that's true.
What happened there? When you said that, no, that was just.
It's, it really got blown out of proportion. So yesterday, Anastasia I was writing this at my flat, and Anastasia was there, and I was like, "Oh, maybe I'll show you the ending." No, I won't. And then do that, and then today, as more and more people are like, "What's the ending?" This has got out of hand. Sorry, I don't have anything more. Yes. Yeah, well, so ours would give you just the areas, so you could split it up in the areas that you do have a lot of data, you would get these conversion results. And the areas that you have like large gaps down between the data set. Or it does give you a conversion of things a large gap. So I guess you could like split the data up with the sections, and you get conversion results in the sections. Yeah, but you wouldn't get any kind of global. It would remain the groups. Yeah. So you wouldn't get any kind of global. Or you would, but this like mini maximum or the maximum distance between data and the maximum and minimum distance.
They also put, you know, they also look for the, like, there where you look at everything, you just look at the. Oh, no, but look at the. Like. Yeah. The nice thing about. Okay, now the books that we look at the. Well, like, and now they look at it, so, yeah. That's important, just. Like, they just put it, this connection in the songs. Yeah, crowd in the space and stuff like this, that crowd space. Yeah, and
All that said, you have to very smooth. A smooth feel to the light out of space. Well, just that I was referring to most fidelity. So one of the cool things about this, like, people use it for most fidelity. So when you have like measurements that are maybe very fast, but inaccurate, and measurements that are very slow but very accurate. So, when you're doing a chemistry experiment, maybe you have online measurements. You have some kind of spectroscopy, which are very fast, you can get every millisecond. So they're not very precise. And then you can do the actual sampling of the experiment and check it maybe every day. And those are very slow measurements, but are very high fidelity. And people use Gaussian exponents, and I think the picture actually shows it very well. Right? Because basically, they're the discrepancy. In the pictures are the discrepancy between the one lower layer and one upper layer. Right? So that's what these moves relatively do. There are kind of corrections. So in the end, what the way that people use these Gaussian processes is the same. And then the Gaussian process would have to correct for the lower. So the fast something but inactive. When you train it with the low but active, you have to correct. So next time that you get fast something, the Gaussian process will have to correct it. This picture shows that. But in this picture, the second layer is the next step. It's not really a correct way. It's like how much the left picture kind of stretches it back.
Yeah, but it's based on, but that's how you do it. So for example, yeah, before you can go to the Gaussian process. One step before that is just to combination. For one day to the year. But you're right.
No, I mean, because we call it experiment, but you're using it more square, like more hierarchical.
Yeah, like I think so. I think there's definitely like that's what again the way that I've seen before people have to like but yeah, I'm sure in terms of like because your functions many times have this problem. Yeah, another thing, for example, many times Gaussian functions are used for and this but sometimes used prediction for control. So it's very typical that people do this what they call model prediction, like a model to predict some variety and then apply one step. It's not just the best thing that people use for control. And then they use Gaussian functions as time series. But then you're actually assuming that the dynamics are the same. Then I think dynamics are one of those today. Probably not exactly the same at the time, or you might observe it. And then this would be very. I actually haven't seen people do like this kind of model because around the two factors. Not even so. But yeah, actually that was right.
As the amounts are sort of because that is something that people sort of
see the other types of information being discussed, if your bounds are not in infinity, and you allow for sort of weird spikes that people like you want to do optimization, say, yeah, thanks. I mean, what do I learn from this? If I suddenly have sort of big sort of spikes because I actually care about this, if your bounds are all in infinity, that part is extremely helpful because you can immediately sort of bound your objective. Often even from the time it's not to that space. So I think that's why, yeah, and that's sort of also really sort of talk about to say this is not what we do.
So why do you think about
I don't really know very much about the convolutional networks. I mean, why would you use this rather than, I mean, I guess that without knowing that much about the specifics of deep convolutional networks, I guess that one of the things is that you can't actually with this, you can actually prove the conversion result, right? You can actually prove that what you're getting is working, you know, like whereas I don't know.
Can I qualify this question without what was on my mind the whole time? Why don't you just like I mean I can see the benefit of a Gaussian process on the top layer of the why not have the rest really like that sort of your data condition. So then for example the simplest case would be exactly my example from before. You have one perceptron, which is just telling you where the switch is. And that's basically the simplest neural network begin as the conditioner for your Gaussian process, which I can totally see why the top layer should be a Gaussian process because then you have lots of normal something like
But would you still get the results if you use this perceptron layer beforehand?
No, I'm just,
like, I mean,
that's exactly what I
that's
said before. So once you look at the condition, Gaussian round field, it's just a Gaussian round field. The one n plus one conditional FA. I'm just saying we make another Gaussian round with that something simple. Well, not simple, something one real fraction followed by an alpha mark. That would exactly the switch where the switch would be to length scales is something that one of the parameters in the neural network, and then also the gradient, and then you
yeah.
Within the Gaussian submodel.
Yeah.
No, but I mean, if you want to make it more hard, then make a full neural network, and then you can have. Yeah, exactly. That's what you said earlier. So I think that would be something interesting to try out. I mean, it would be more interesting to try out. Nothing asked before. It's like to try out. Because this question, like you said, everybody will ask me why you're not using neural network. You can try out a neural network and see. As an example, theory comes.
That's a good idea. I mean,
It's not.